hand over to you, Rod. Thank you very much.
Thank you, Simon. Hello, everybody. Good to sort of see you. Welcome to our little seminar here on infrared heating. So, as Simon says, I'm Rod. I'm co-founder of Energy Carbon. We manufacture a range of infrared heating products and also decentralized low energy MVHR products, which is something that we'll probably come back, I think, Simon, at some stage and do a little talk on those later on. But for today, what I want to do is give you all an overview of infrared, what it is, because a lot of people think they know what it is. Some people haven't got no idea, and some people are experts, but I'm just trying to level it all out. Talk about what infrared is, talk about the different types of infrared that are available on the market, what the pros and cons are. Then obviously I want to introduce you to our product, where it all came from, what we're about, how it fits in, and you'll probably find as we're talking that there will be lots of points in there where you think to yourself, oh, I could use that for my garden shed, or I could use that for my bathroom, or like Simon says, I could use it for my basement. And there's a lot of parallels with the stuff I'll show you. And I don't think there's a day that goes past where somebody doesn't say, oh, I could use that for my building. And that's the beauty about this type of system. It is very, very flexible. And I'm hoping that's what will come across today. So welcome. Bear with me. I'm not very good at doing these things, so I'm going to hopefully do this smoothly and in a sexy manner. Here we go. So this is our manufacturing plant. I thought I'd just show you this just to see, because there's a lot of snake oil salesmen out there. There's a lot of infrared types of products out there that come from China and from sort of dubious places. But this is our manufacturing plant. It was established in 1881, £62 million net worth business. And this is the top picture there. We manufacture there 1 million linear meters a year, which is enough for 25,000 homes. And the bottom picture is a facility. It's another one of our partners who have I like to call it the science lab, because this is where we come up with new products. So this is testing, this is certification, that type of stuff. And then the little building on the right there, which is actually quite big, is our storage facility. So we have what we don't have a problem with is coming up with the stock. You know, we've got plenty there. And the 10-year warranty that we give with the product is with the German manufacturer that you see there. So it's an ironclad warranty we're giving. I thought it's just worth sharing that at this stage. And I'm going to tell you a bit more about their story a bit later on. Now, what is infrared? I like to show this little picture of a girl touching the pavement. I'd like to say we experience this a lot in the summer in England, not at the moment, obviously. But we're heated from above, aren't we? The sunshine comes down. As soon as those clouds part, that warmth comes down. And although the air temperature doesn't change, we do feel the temperature of the pavement starts to increase. So you'll find that on a sunny day, the tarmac or the sand or the concrete starts to warm up from the sky above us. That's infrared, and that's what we're dealing with here. So this is a sort of a little graph on what we're talking about with infrared. Infrared is a light wave, and light waves come in many forms. They go from gamma rays right the way through to microwaves and everything in between. So X-rays, UV rays, the visible light that we can actually see, and then infrared there towards the end. And all the other rays, you know, the UV rays and the X-rays and the microwaves, we can't see them, but we know, you know, we get that they work, don't we? We understand that if we go to hospital and we're X-rayed, it's going to see through our body. We understand if we put a jacket potato in the microwave, it's going to cook the jacket potato. But people have a difficulty understanding and believing in the infrared spectrum and the infrared light wave, because it's doing something that we want to be useful in the home, but we can't see it, but we use it all the time. And we split infrared down into different components, different terminologies. Now, if you think about all those light waves at the end, the gammas, the X-rays, the UVs and the microwaves, that's all dangerous stuff, but useful. When we come down to the infrared spectrum, it's a very narrow spectrum of light. It's between 0.76 micrometers, we're measuring micrometers, to 1,000 micrometers of light, and it's split into 3 sections. Those sections are near infrared, medium infrared, and far infrared. Now, we think of In fact, I'm going to come on to this in a bit more detail in a second, but those three things I'm going to talk you through what they mean and where you see them. But when we break down the far infrared spectrum a bit further, the infrared, the light spectrum that we're interested in is a very narrow field. You see on there, it's between 6 micrometers and 50 micrometers of light. This is the bit that we're interested in. This is the bit that heats the human body most effectively. All right. And then we go further on down here. We've got the human body emits infrared at 10 micrometers. So we're actually giving infrared off of our bodies as we're sitting here, some of us more than others. So near infrared, let's break that down there. So near infrared, we're used to seeing those outside patios or outside pubs in the form of patio heaters. So we'll know that as soon as we stand under them, we're going to feel the benefit of the heat. So instantly we'll feel warm, but if we step to one side, we'll feel cold. We also know that we can see it. It burns bright red. And we also know if we touch it, we're going to burn ourselves because it's burning at an intense heat. That's your near infrared light. You can't really use that in the home, but you can use it in the gardens and some commercial applications. The mid-infrared spectrum takes that slightly to a safer degree. It's not quite so aggressive. And mid-infrared is used for things like sports therapy, physiotherapy, that type of thing. So if you've got a knotted muscle after playing footy on a Sunday, you go to the physiotherapist and they'll get a light out, won't they? And they'll put it on your skin and massage you with a red light. And that's sending that mid-infrared light wave 2 inches into the skin to soften that knot out before they attack it with their evil hands. And then we've got far infrared, which is that little bit that we're interested in. Far infrared is beneficial to humans and all living things. It's around us all the time in the form of the warmth given off by the sunshine. It's something that we crave. And I'm looking out my window now onto my little bit of sunshine, and I can see my 2 dogs there lying on the patio. They're not lying there because they want to get brown. They're lying there because they're absorbing that lovely infrared. Because animals instinctively know, we instinctively know that we go in the sunshine, we have a better feeling. We have a feeling of well-being when we're sitting in the sun, most of us anyway. So that's the part that we're trying to recreate with any heating system. We want to make it so that it's not as aggressive as near or mid, but it's closer to the far infrared spectrum. The human body, now I think we all probably all have heard that the human body gives off 100 watts of energy when we're sitting there in our homes and our offices. So put 10 people in a room, that's a kilowatt of heat. The more people in the room, then obviously the hotter that room's going to get. That heat that's coming off the human body is actually far infrared at that 10 micrometers light range. We are actually producing far infrared ourselves. So when we're feeling cold in a room, why are we feeling cold? You know, you kind of need to get your head around the thing of what thermal comfort is all about. We've got a slide on this in a minute, but actually, as we're that feeling of cold is actually that infrared energy leaving the body. And what we do traditionally in heating is we don't actually replace that. We put a big bubble wrap of warm air around the body to stop that energy leaving the body. And that's what gives you the feeling of comfort in your home. So it's the warm air trapping that infrared light from leaving. But actually in an infrared heating system, what we're doing is actually replacing that energy as it leaves the body at almost or as close to that micrometer range that the body is emitting it, so that body instantly receives that heat and you can actually feel it being replaced in a cold environment. Is it safe? A lot of people say to me, well, is this safe? It sounds wonderful, but isn't it microwaves or gamma rays or anything else? Yes, as we've seen, it's on the light spectrum, but actually, no, it's perfectly safe. As I said, our bodies create it. We've used it for years and years in newborn baby incubators to warm the babies. And when we're putting it into things like an incubator, we're not doing it just to keep the baby warm. It's doing things like it's relaxing the baby in that little incubator. It's actually creating a better blood flow. It's generating more T cells, so their immune system is being boosted. It's got a lot of other health benefits around it. I'm not suggesting we get that with a heating system, but you know, you can see it's a safe thing, and there are other implications of having far infrared in the home. So how do we create far infrared? We've talked about it already been created through body heat. Sunshine obviously provides it. Commercial applications, we've been trying to create far infrared now since the 50s. In fact, sorry, we have been creating far infrared since the 50s, predominantly in China and the Far East. And the way it has been created in the past is by heating up things like rock or glass or ceramic. And when you heat those substrates up to extreme temperatures, and I'm talking 200 or 300 degrees centigrade, they then emit the far infrared at that frequency we want. And I suppose a parallel to that, or something to give you an idea of what that feels like, would be sitting around an open fire, sitting around the campfire, and you feel that warmth coming off of it, and you're being bathed in the far infrared heat, which is the radiation from the fire, and that's been created by the burn of the carbon from the release of the carbon from the fire, from the wood, and so on. Now, 300 or 400 degrees in a heater is not particularly safe, as we've already said. So we looked at other types of materials to try and bring that temperature down. And obviously, by bringing the temperature down, we're also bringing the energy requirement down as well. If you imagine you're trying to burn something at 300 degrees, that's an awful lot of electricity being used. If we can bring that temperature down, we're using less electricity, aren't we? And we found over the years that different types of products have a different emission of far infrared. Everything is carbon based, as we know. So different types of carbon will give off a different power level, or require a different power level to release that far infrared. And more recently, I suppose probably about 10, 15 years ago, it was realized that graphene, probably longer than 10 or 15 years ago. I'm showing my age now. It's probably more like 25 years ago, actually. So graphene inks were used because graphene is a pure form of carbon, and that was used to create far infrared on a film basis. But you still had to get that to sort of 60 to 100 degrees to create the far infrared. Now, we've recently found, I say recently, about 2010, we found that we can actually heat carbon to actually 35 to 40 degrees if we get the voltage right, and release our far infrared light signal at almost 10 microns. It's about 9.4 we're emitting on our products at the moment. So it's almost that sweet spot of light we want to get. 35 to 40 degrees is minimum amount of energy, and it's also safe. You know, it's body temperature. You can touch it without any problem. So that's where we are. That's where we are now in the manufacturing process as an industry. We're pretty much hitting that sweet spot. I think that's that one. Right, I'm going to touch on this thermal comfort because I'm not sure how many people out there understand what it is that makes you feel comfortable in your house. It's always worth revisiting this anyway. So we've got 5 points there. We've got clothing and insulation. Well, I can't affect what people are wearing, and I can't affect the metabolic rate, apart from saying, come on, jump up and down and feel warm. We know that if we jump up and down, we're going to feel warmer. So those are 2 obvious things. But the other 4 things on there are things that our control systems or our heating systems can affect. Now, we all know about air temperature. A convective heating system will pretty much only attack the air temperature in a home. Radiant temperature, what we call mean radiant temperature, is the surface temperature of objects around you. And if you're sitting at a desk now in your homes or your offices, I invite you now to, if you've got short sleeves, put your back of your arms on your desk and feel your desk. And you should feel that your desk or your stone worktop or even the sofa or the chair you're sitting in feels colder than your body temperature. And that's even on a summer day, or even when the house is at 21 to 25 degrees. That temperature of that desk or that leather sofa you're sitting in can feel cold to your skin. And that has a profound impact on the thermal comfort of the room, or the thermal comfort you're feeling from the room. So mean radiant temperatures high up there along with air temperature. Air speed is something that you don't really notice, but your skin does notice. And we sometimes have that phrase where somebody's just walked over my grave, or I've got shiver, the hairs in the back of my neck are standing up. This is when you have a convective system and you've got your warm air rising and the cold air coming down, and you've got a microclimate of hot meeting cold, so that's creating dampness, which I was going to come on to in a second. It's also creating an air movement, an air current in the air, and your skin is picking up on that. Finally, as I said, relative humidity. So as that hot air is rising, the air molecules are getting bigger, they're picking up more moisture from the air, and then they're traveling around the room, and your relative humidity goes higher in the room, and your body feels damp and clammy. That warm air will eventually touch a cold surface, as we know, and cause condensation, which then leads to mold and all the other problems we're seeing in buildings, particularly in modern buildings now. And of course, when it drops down again, when it cools down again, we're dropping down. We have dry air then, so we're getting a dry situation in the building, and that's when we're feeling sort of itchy skin and dry nasal cavities and all the other things. Now, I'm telling you all this because infrared addresses all of those things. Infrared will give you a balanced relative humidity. It will give you no convection in the air, so you're not feeling that air current. Gives you perfect mean radiant temperature, and it gives you a good air temperature in the room as well. Eventually, that air temperature becomes last. So that's where we're slightly different, very different from everything else. And I'm going to show you some test studies later on that demonstrate how all this comes together. There's some little pictures here. That's back when I moved into this house. Before I've actually got I'm working in my little home office at the moment. Despite the background that looks very fancy, I'm in an old Victorian house. When I moved in here, I had radiators, and that's a picture of behind my radiator. And I think we're all used to seeing that in our homes, aren't we? That's the dust that's been dragged along the floor and then kicked up through those vents in the radiator and thrown into the air in front of the window. And we often see that on a sunny day. We see all the dust dancing in the air, and it's going all around the top of the building and landing the other side of the room and going around the big cycle. And you're breathing that in. You know, it's not very nice, is it? It's full of dust mites, it's full of crap, it doesn't smell very nice, and it's in the air, it's just hanging there. That's the effect of a convective heating system. That's something that we're not going to get with infrared. So we're warming the air. This warms the air first, obviously. It creates the moisture we've talked about, a little microclimate in the air. And you get stale or we get damp air in there. And you know, I've got a 92-year-old mum. She's in a care home now, bless her. And you walk into that care home where they've got the heating ramped up to about 25 degrees, and it's just stuffy as hell. You can't spend more than a couple of minutes in there. So we are actually at the moment converting a few care homes over to infrared because they'll have fresh air in the room, but it will still be warm and comfortable. Conversely to that, with a radiant heating system, like with infrared, we're not warming the air at all, but we are eventually, but we're not aiming to warm the air. We're warming the surfaces and the occupants directly. We're reducing the moisture in the air, which is what we talked about already. In fact, it dries the air out to a certain degree, but to a healthy level, so you get balanced relative humidity around 50 to 60. Minimum circulation of dust and pathogens. Again, in that situation with the care home, if you've got somebody with COPD or asthma, you know, it's a perfect situation to put infrared in there because that's going to stop the aggravation of that. And in fact, I don't know what the percentage is, but it's going to be 50% of the population now suffer with asthma, don't they? So to have an infrared heating system is going to make your breathing a lot easier. There's a picture of a mountain there, by the way, because I like mountains. Problem solved with infrared. We've already talked about dampness, but I think it's worth revisiting this because it's quite critical. So in infrared, if it's put into a room correctly, it will warm all the walls and all the surfaces before it warms the air. Okay, I'm going to say that again. It warms the walls and the surfaces before it warms the air. It warms the air because all the walls and surfaces are actually the things that are warming the air. The infrared doesn't touch the air at all. It bypasses the air, and that has two benefits. One, it gives you fresh air, and two, it cuts down on the energy. What's the point of heating a big bubble of air when you can get straight to the end product, cutting out the middleman, so to speak? You're warming the person directly, warming the surfaces. When it warms those surfaces, that mean radiant temperature, that gradually that becomes an emitter, and that gradually warms the air around you. So it gives you a very gentle warming of the air, rather than a radiator banging it out at 2, 3, 4 kilowatts in a room. It's a gentle overall warming of the room through the surfaces, a bit like underfloor heating, I guess. that does the same thing, doesn't it? It's a very slow rise of the air temperature. But what that means is you're not going to get condensation if you put your condensation on the walls. Condensation equals damp, as we know.
Colin King, who spoke a few weeks back, and will be speaking again in October. He's from the Centre of Moisture in Buildings, and he was saying, unprompted, he was a big advocate of infrared, because obviously notices that you don't get the same moisture issues and damp issues through it.
Yeah. And we're going to come on to the differences between different types of infrared heating system, because actually they can make it worse, Simon. Some situation can make it worse. So you have to be very careful about placement of your infrared. And also you still need to think about in the building envelope, where we're making a building airtight, we need to think about extraction and ventilation as well. You can't just rely on infrared by itself. What that will do is make sure you've always got warm walls, so those walls are protected, but you still need to extract it as well. So that's why a good NVHR system will work in unison with something like an infrared heating system to give you a good balance. I've missed the bed bugs, because I think we all get the point. Dust, bed bugs flying around in the air, so I'll leave that one. I'd rather take questions. This is an interesting one. I only received this a couple of days ago. So you may all have heard of a company called Wonderwall. Wonderwall manufacture a smart control system, and they also install that into homes alongside an infrared heating panel. The smart control system manages batteries, it grid balances, and it does all these other things. It's got a smart hot water tank, and it's a whole house system. And we're all moving towards that. We have our own whole house system launching soon as well. But they did a trial. It's an ongoing live project. 20 homes down on the south coast, all lived in by a range of different families. In fact, one of them there is a potter, and he's got a kiln burning in there. And 3 people in the family, 3 families have got hot tubs going. And they've conglomerated or amalgamated, not sure the right word is, all of those energy costs. And they've come up with this little graphic. Now, I received this 2 days ago, and I went, wow, look at that. Your SAP calc, if you average this out across the 20 houses, your EPC, your SAP calc is coming out at 3 kilowatts. That was the predicted energy use in those homes. They're coming out on average as 1,433 for the heating system, 1.4 kilowatts. Now these aren't tiny houses. They're fairly big houses. They're about 90 square meters. So good size 3-bedroom average sort of family house. We've got hot water in there. Obviously, we need to think about hot water with infrared, don't we? Because we're not heating the water, and I can address that separately. Got hidden consumption here. Look, 4.2 kilowatts of hidden consumption. That's your cooking and washing machines and all that type of stuff, which aren't actually factored in. And then we've got export back to the grid and this type of thing. But on average, these homes costing £1,200 a year for everything. That's including the hot tubs and everything else. So that's pretty good actually. And it shows that with an infrared heating system, you can actually, on a 90 square meter house, get away with 1.4 kilowatts a year. All right, so you can. In fact, this is saying on there it's similar performance to a heat pump, and we're doing a thing with Hawkes Architecture. You know Richard, don't you? You work with
yeah, they work with us. Yeah, we work with them. Yeah. We're
working on them on his calculator tool. I don't know if Richard's on here.
No, he's not on the call. No.
So he's working on a calculator tool, and I had a good old conversation with him on why it is that infrared is energy saving. What makes it energy saving? We all quote 30%. We can say 30%. We can say 50%. Yeah, well, prove it. There are 50 papers out there on infrared. There's a literature study bringing those 50 papers together that demonstrate how infrared is more efficient and how you can save that 30%. Part of that 30% that's bandied about is based on those factors of thermal comfort. Every time you have that need to, or that feeling of that cold desk or that damp air or that air current, every time you feel that, it makes you want to reach for the dial and turn it down. Conversely, by having those things ticked off, it means you can adjust your heating down by up to 5 degrees. Each degree, as we know, is 6% energy saving. So, that's one of the factors that makes infrared more efficient. Another one, obviously, is the fact that you can turn it on and off as you need it. It's reactive, isn't it? So it reacts fairly quickly. So that's another thing that's affected this here. But also it's also the amount of energy, as I said right at the beginning, that we're using to create the infrared in the first place. We think of thermodynamics. If a room needs 2 kilowatts, it needs 2 kilowatts. People always quote. Not with infrared. With infrared, it's a different system. We don't look at calculating heat loss in a room in the same way that a conventional heating engineer would look at calculating heat loss. I'm going to throw that out there, and I'll probably have people tutting and shaking their heads at the moment, and I'm used to that because it's a bit contentious. What we look at is we calculate heat loss in the same way. So we take U values, we take square meterage, we work out the heat loss based on the geographic location and the direction of the building and all the other things that you work out a heat loss on. But we don't work out the cubic meterage of the building because we don't need to worry about the air in there, do we? We're not heating the air up. So we don't look at the cubic capacity in there. We look at the square footage. So we take that heat loss and we take it down by the ceiling height. So if you've got, for argument's sake, to make it nice and easy for maths, you've got a 30 or 300 square, a 300 heat loss, we can take that down on a 3 meter ceiling to 30 heat loss, if that makes sense. And then the most important thing is we're looking then at coverage, and we'll come on to this later on. It's making sure that you're thermally comfortable within that room. We're not looking at the air temperature, we're looking at making sure that wherever you walk in that room, you're feeling that radiation bathing you and all the surfaces are equally warmed. That is more important than working out the mass of the air and working out what the heat loss is. So all of those three factors coming together mean that we can get good energy savings.
Do you get like cold spots though? Because if you're not heating the air, then you're reliant on the furniture in the room to be the conductor of the heat. If the fleece or the panels are not pointing in a certain place, does that mean that you're going to end up? So when you walk into a room, you would still potentially feel cold.
Yeah, absolutely. Yeah. This is why, and we're going to come on to this in a minute, Simon. This is why not all infrared products are the same. You need to think about how that infrared is working and where you position the infrared. So you're absolutely spot on, and we'll come on to that in a minute if I can. So this is that. I think that's quite a useful thing. That we've got testing in Germany as well. For example, we've put it in test houses out there, and we're showing a fairly about a sort of a running on a par with an air source heat pump by the time you take off costs like maintenance and that type of stuff on there as well. So we can start to balance things out overall. This is good old Hawks. I love this. I'm not going to go into any detail on this, but to me this just sums it up really. And you probably can't even see this because Richard and his team, I don't know whether you're involved in this, were you, Simon? They've done a 100-year graph to show what would happen when you plot out a gas boiler or a heat pump or infrared over 100 years and what the cost would be in terms of embodied carbon and also running costs on there. And the point of this is that every, say, 15 or 20 years, you have to replace your air source heat pump. You have to replace your gas boiler. Every 15 or 20 years, that gas boiler, that air source heat pump comes with embodied carbon, doesn't it? So we're saving on operational carbon because of that COP of 3, but we're actually hammering the ecosphere, or whatever we want to call it, on embodied carbon by replacing it, by maintaining it with people running around in vans and all the rest of it. So we start to catch up with infrared because with an infrared system, you don't have to maintain it and you don't necessarily have to replace it very often. Certainly our product has a design life of 50 years. A lot of others on the market have long design lives as well. And then he's put down here, where do all the worn out heat pumps end up? Question I often ask myself. If we're going to achieve our 600,000 heat pumps a year, I mean, that would be amazing. I can't see it happening, but if it was, 10 years time, 15 years time, that's 600,000 heat pumps coming out, plus all the ones before that. And they've all got to go somewhere, haven't they? All that refrigerant, all that R32 or whatever it is that comes out, and all that aluminium, everything has to be recycled somehow. So we need to set all that up as well. So it's a massive, massive challenge. And every time I look at any other form of heating system, I look at how complicated it is. And I hope by the end of this little talk, you'll realize how easy it is to install an infrared heating system, the benefits you get from it. And then you'll look at anything else. You'll go into a building, you'll get your plans out for a new set of designs you're doing. You'll think, you know, why are we going to all that effort to put this type of heating system in? Because we're sold on the idea that that works better than that. When actually, when you weigh up all these other things around the fuzzy edges, it starts to make less sense.
Have you ever been on a panel opposite someone like Graham Hendra? I mean, we tend to talk a lot about heat pumps on meshwork, and there's a bunch of good guys that advocate them, sing their praises, and you know, Graham being one, and Ryan Filk from Daikin, and a whole bunch of people with Nathan Gambling, etc. Yeah. And I'm just, it tends to get to a point where it's like us or them. There's a bit of And I mean, there's obviously a wider issue going around with sort of replacement of gas boilers, and that's the big issue. And yeah, I like this because it does seem simple, but I haven't experienced it, and I suppose that's the big challenge of where IR is in the market. I mean, in terms of adoption, there are more heat pumps than IR installations. Is that fair to say?
Oh God, yes. Yeah, absolutely. I mean, the heat pump market. Don't get me wrong, Simon. Heat pumps are fantastic. You know, if I had the right house for it, I'd put a heat pump in all day long. But I would run it alongside infrared. I would have the two together if I can afford to do it, because you get benefits from both. They both work in different ways and in different styles. You know, so they both work really well. What I'm saying is, a lot of the buildings that we look at, a lot of the plans that people send us, a lot of the time when I'm walking down the high street and I'm thinking about the problems we've got, you know, in fitting our buildings out, I look at them and I think, I could send a team in there and I could have that done in a week. I could send a team in there, I could have that done in a day. I could get the stock over tomorrow. Well, maybe not tomorrow, but I can get stock sent over in a couple of days. I've got engineers, you know, I can get anybody to fit it. Electrician, the plasterer can fit it. Now, all these things are ironed out. I'm not saying on the job it's much, you know, you still have to put cabling in, you still have to whip out old radiators and things like that, but it becomes a lot less complicated. And I do think there's room for, there's a need for everything. But at the moment, I saw, and I don't get annoyed because I'm too old to get annoyed now, but I do occasionally think to myself, where's the balance, you know, in this? And I saw a little thing this morning, somebody put up about a new heat pump training van that's going around, and it's a mobile heat pump installation centre, being funded by the Scottish government. Okay, lovely, great. That's going to help train new engineers for heat pumps. Where's the balance in that? There's no government funding coming to infrared for us to do the same sort of thing. The funding is all going towards pushing the heat pump all the time for heat pump manufacturers that have billions of pounds worth of net worth anyway. Do you know, we're funding these massive, usually Chinese or Korean conglomerates to manufacture these pumps and bolster their bottom lines, but not balancing it out with other products or other technologies that can address the situation. Maybe not as well because of that COP, but certainly better in terms of comfort levels, embodied carbon, and time on job, and cost to put it in. Anyway, I'm going to run out of time if I'm not careful.
Yeah, sure.
So different types of IR products. We've got there, top right there, you can see the infrared panels. I think we're familiar with infrared panels. Now you can see there, Simon, you talked earlier about positioning. You can see there, you're going to put an infrared panel there and an infrared panel there, and you know if you sit underneath those, you're going to feel warm, but you also know if you go over here, you're going to feel cold. Positioning is not brilliant there, is it? So this part of the room, I don't think is going to be particularly warm. So normally what they do is they position these over a sofa or over a dining table. That's probably what they've done here, actually. This is probably the lounge, and that's probably the dining room. This is the mid-infrared heaters. They tend to go into commercial applications or bathrooms and this type of stuff. So more reactive patio heater type stuff here. Infrared laminated films, underfloor heated films. This is what people confuse us with. This is the side of the market, this bit here, and this bit, people understand these two here, don't they? They're functional. If you want to heat your garden up, fine, that's brilliant. We don't question that. These two products here have come with lots and lots of problems in the past, and because of that, we're left with the legacy of those problems, and we're kind of trying to ride that a little bit, I think, as an industry. Then we have the fleeces, which is what we manufacture here. So if you look at how an infrared panel, for example, will work, if that's your infrared panel on the wall, or that could be flipped over so it's on the ceiling, we're getting to about 90 degrees. So you've got yourself a piece of graphene buried within the panel that's fed with 240 volts, which then emits out over a panel. That panel, if you touch them, will be hot to the touch. You know, between 80 and 100 degrees surface temperature. I've seen some going up to 200 degrees surface temperature, and they were proud of that. You know, and you're going to mount that on the wall. That can burn your skin, can't it? 90 degrees. I haven't got any children anymore because I'm too old. But you know, if I did have children, I wouldn't want them touching that. So we start to put them on the ceiling. Put it on the ceiling, and again, you put that over. You put that over this area here. That directional heat is going to come down and warm this area here, but everything else will be cold. Now the trouble with that, as I said, you walk either side, you've got cold. Either side of that, you've got a convective system going because you've got convection going on there on the edges. And you've also got cold walls here and here, and maybe warm ceiling, warm floor, you know, in that particular area. So you're still going to get damp issues in that room. So you'd have to balance it with two infrared panels. And, you know, not a lot of people do. If they say they need 800 watts in that room, they'll put an 800 watt panel in. But actually, from a coverage point of view, they probably need to put 1.6 kilowatts in because they need two panels to spread the energy. So they're directional, low spread with those. Correct placement is required all the time. They can be unsightly if they're on show. There's a danger of plaster disintegration. Now, early on in our journey, we consulted with Knauf and with Gypsum on various things. You know, that they're part of our partnership early on. And I don't know if you're aware, but warranties are affected if anything touches the plaster over 50 degrees centigrade. So if you start to put things in the plaster work, it's over 50 degrees, it can damage the plaster. You've got risk of delamination with these sort of products here, the films. You've got a copper strip either edge. You've got graphene printed onto a laminated film. That gets put through a laminating machine. And as this heats up and cools down, these can start to decouple. And when they decouple, they can get failure. You can get hot spots if you cut into it and screw into it. It'll still work, but you get hot spots. So that temperature might go from 50, 60 degrees up to 200 degrees in the spot where you cut it. You know, these are problems that the industry sees. A lot of these things, these films and things, when they're hidden in the walls, are at 230 volts. You know, you don't really want to be putting 240 volts behind the plaster work in a wall or a ceiling, do you? Because I know I would stick something in it, I'm sure. And these are the sorts of things you need to think of. You need to have a bit of common sense when you're specifying an infrared heating system. Think about the things I've said. Think about the surface temperature. Think about that radiation, that quality of radiation you're getting, that micron range. That's a question you need to ask. What's your micrometer range on your infrared heating product? What's the surface temperature it's going to get to? Is it 230 volt? How are you mitigating against people being electrocuted? What happens if it gets damaged? What's going to happen about repair? You know, all these things, just like anything else, you need to think about the common sense answers to those or ask the questions. Let's talk about SAP, SAP, EPC, those types of things. Well, infrared is crap, quite frankly. Infrared doesn't get factored at all in EPC. In fact, it negatively scores EPC. This is another reason why we haven't got the same traction as heat pumps have. All right, it's helped since we've had the new release of SAP. Have we got the new release of SAP yet? I've got confused now. It was due out in June, wasn't it? Then July. I don't know whether it ever came out.
Cool, must know.
So, I mean, that was supposed to have helped a little bit more. So what we have to do, we have to work harder when we're building a house or retrofitting a house than you would do with something like a heat pump. With a heat pump, you can put it in, you get such a good SAP score, you get a decent uplift on your EPC straight away. With us, we have to make sure we've got good fabric, first of all, not just because it does help, but also because it gives you a better uplift in your EPC and SAP. We have to put on some PV on the roof, probably about 4 kilowatts for your average size house on a roof. We have to put in a smart hot water tank. We align ourselves with Mixergy, and I'm sure most of you know Mixergy by now.
Pete spoke a few weeks ago. He was actually talking about this issue as well, and that they're frowned upon from an EPC perspective, and they've tried to sort of speak to the legislators and getting nowhere, and it's just banging your head against a brick wall, really. So frustrating
as hell, isn't it? Frustrating, but things are changing though, Simon, and I will have an announcement to make in a few weeks' time, which I'll tell you about later on. And
that's where it makes a difference to all the landlord and the rental properties out there as well, because if they're being encouraged to increase their EPC ratings to C, and this is a simple solution, but you don't get a benefit from an EPC perspective, which is legislated, then the landlords are in a tricky position. Rich has just confirmed that the latest SAP is out as well, by the way.
Oh, okay, yeah, I did wonder. So what we have to do is what I'm saying is we have to take a holistic approach to a retrofit or a new house, which means that house that that owner moves into or moves back into has got a better house, in our opinion. They've got lower energy bills, they've got grid balancing, they've got battery storage, they've got we have to put those things in. That puts the cost of the house up, but the cost of the infrared is less. So the savings you get from installing something like a heat pump, for example, is we can apply it to all these other factors to mitigating SAP. And we have got some of our houses, our retrofits, and some of our new builds, we're getting A ratings on, but we have to work hard at it. So it can be done. You have to make sure you've got a good SAP assessor, not a lazy SAP assessor, because I have seen a lot of lazy ones who are just happy pulling down the default values on their tools. So it's good to make sure you look at that in detail. Things that are restrictions with infrared, we've got anything with a heat loss of 70 watts per meter squared. For example, if it's less than that, it can be overly expensive to run because it's on too long in a day. And ceiling mounting isn't suitable for heights in excess of 3 meters. So an infrared light signal, if you imagine shining your torch, the more batteries you've got in your torch, the further that light beam is going to go. We're all like a big man torch, don't we, which lights up the trees. The more powerful your infrared is, the further that light beam is going to go. But on average, about 3 meters is where it maxes out. This is us now. Okay, so that's infrared generally. I'm going to whiz through what we're doing. First of all, our product is made from recycled materials. So in Germany, those factories I showed you earlier, they manufacture a lot of stuff in carbon fiber, as do the automotive and the aeronautical industries. All that carbon fiber is going to landfill. They all got together as a bunch of industries in Germany and thought, what can we do with all this carbon fiber? So they put a competition out for the universities to come up with a solution. Stuttgart and Dresden came up with the best bids. They set up 2 science labs in that big factory I showed you, and they had a 2-year competition running between the two universities. Stuttgart won it in the end. They looked at all sorts of stuff, but one of the things they did look at was the Korean heating system. Now, in Korea and China, in the 60s, 70s, and 80s, they were moving across to graphene laminated films. They had problems with it, with the delamination, with fires and buildings and stuff like that, where it decoupled. And so it got banned in government buildings out there. We had all the problems with cutting holes in it and everything else. So Stuttgart looked at that and thought, okay, in principle, if you vibrate carbon with a low voltage of electricity, we can get far infrared and heat our buildings. Let's see if we can do it in a different way. Let's see if we can extract the carbon from that carbon fiber and use that. It's not as pure as graphene, but we should be able to use it. And what they do is they mulch it down into nanofibers, so tiny little particles. They take the copper and mulch that down as well, and they squish it together. That's a technical term, squishing it together. It's called homogenizing it. So it squishes it into one piece of fabric. And that fabric then won't delaminate. And because of the way it's made, you can cut holes in it, you can screw into it and everything else, you can cut into it. And the energy won't rush to those damaged areas. They find a path around it instead, as opposed to rushing. So if you do that, you still maintain the average temperature in the fabric. Also, they found that if they drop the signal from 240 volts to 36 volts, not 24 volts, so we do have a 24-volt product. Dropping it to 36 volts, we can get that temperature to create that far infrared light wave down to about 35 degrees behind the plasterwork. So it means that we're not going to invalidate any warranties and it's safe to the touch. That has a problem, I have to say, because quite often people don't believe it's on. So you have to you have to get a FLIR camera out, or just, I always say to people, are you comfortable? Yeah, well then it's working. That's all I need to know. So this is where this has all come about from. So this was 2010. That all happened. And then since then we've got different iterations of the product for different building solutions, really, which I'll come on to. So it emits from 3 meters from source. We can take a room temperature up to 27.6 degrees if we want to from the ceiling. The reaction time is 3 minutes. So what happens is you turn the system on. Once it comes on, it takes a minute for the transformer to kick in for that 36 volts. It then takes 3 minutes for it to reach the 30-odd degrees temperature on the mat. That then starts to create the light wave, which then comes through at 10 to 20 microns. It's more about 14 micrometers. And it then sends that light signal through plaster 3 meters and starts to warm the floors within 8 minutes. So the floor temperature will start to come up 8 minutes onwards. With our DryTech solution, it comes up 11 minutes onwards. It's 0.4 millimeters thick, so it doesn't have any impact on basements like yours there, Simon. You can still maintain a low ceiling height. And we hold the worldwide manufacturing right on this now. So this is a worldwide patent on this, so nobody else can make this product because we're greedy. So that's the product. And this is what we've done with it since. So this is the fleece. I keep pointing at my screen, I need my mouse, don't I? This is our base product. We have this now in 3 different iterations. We've got our core product is the 110 watts per square meter. 220 watts is where we're struggling with heat loss in a building. So in a Victorian leaky building, for example, or a farmhouse or something like that, we'll put 220 watts in. If we go into something like a Hawkes building, we've done several Richard Hawkes stuff, passive house type buildings, we'll put 60 watts per meter squared in. And the reason for that is so that we can spread this over the ceiling area. We want this to cover between minimum of 30% to 60% of the ceiling area, to address your question earlier, Simon. So when you walk in a room, you will feel that benefit wherever you go, not in two little spots. Normally with an IR panel, it's covering like 5 to 10% of the ceiling area. So we're covering between 30 and 60% with this. So this gets plastered in either to the ceiling using multi-finish plaster. It goes into walls. We don't like walls as much. Ceilings are better because we put it in the ceiling at 60% and it will cover 100% of the room. Put it in the floor, you've got to cover 85% of the floor, because you're going to get cold spots in between where you're walking in bare feet. And also you're going to put a rug on it or a dog bed and you're losing the energy. Put it in the wall, you lose energy. In the ceiling, we don't do anything up there, do we? So ceiling is better. And if you remember that girl touching the ceiling, touching the floor earlier on, that's what we used to. We're used to being heated from above. That's what happens in nature. That's what we're designed to accept. So it feels more comfortable. We then have this product here, which is for dry, for where we're not using wet trades. So this has got a carrier either side of it, and that's designed for stapling through that carrier direct to the joist of a building. And then all you do is you've got your bare joists in the building, and you roll it out and staple it on. The electrician crimps it up back to the transformer, and then you dry line on top of it, and then you just tape and joint on top. So that's a super fast fit. And this is a PET, which is used under carpets and laminates. Incidentally, the fleece we can put into screed as well in the floor if we want to, under tiles and things. And then we have what we call Protect. Now this is an interesting one. This is designed originally for putting around window reveals to keep condensation down in walls, and we can attach this to a moisture sensor and it'll kick in and out and keep the wall above dew point. You can actually do the same with all of these as well. So if you've got a wall that is really difficult, again a basement or something that it's always damp, then you can put this into the wall and connect it to a moisture sensor, and it will keep that wall dry. So those are our core product offerings. We've got a new one that's launching in 2 weeks' time, which is a drop-in ceiling tile, 100 watts per tile, really cheap, really energy efficient, but super comfortable. So no longer will Sharon or Karen or Fred or Mike have blow heaters at 2 kilowatts between their legs under a desk, keeping themselves warm and keeping everybody else too hot. You can then drop in these ceiling tiles instead. That's launching soon. This is our testing with Bisra. We did this a couple of years ago, so I'm just going to rush through this. This is Dry Tech. This is the fleece product, 1.5 meter from the floor, so that's sort of head height. This is seated height, this is floor height. So if you take the ceiling height, from turning it on, it takes 3 minutes for it to reach the surface. So surface is being your head, basically. It takes 1 minute for your body to feel it. This is the globe is the body. And it takes 10 minutes for the air temperature to start to come up. When you look down at the floor, again, 8 minutes to start to warm the floor, 10 minutes to warm the air. So the air temperature is rising fairly evenly across the room, to address your point earlier, Simon. But it does always mean that those surfaces will, as I said, will always warm up before the air does, which demonstrates why you're going to get that relative humidity.
Yeah.
Right.
Actually, sorry, Rod, can I just interrupt just because we are going to be running out of time, and also we've got a question, and it relates to comfort, and I'm not sure what the first name is, but Odanella, as on Zoom, says is asking, I'm aware that human comfort tends to prefer warmer feet and cooler head. Was wondering how IR in ceilings interacts with this. Does the warming of the ground surface avoid the feeling of colder feet than heads?
Well, we warm the floor as well. You know, we've got one of the houses I was going to show you later on if we get time is one that has marble floors. It's a nice luxury home, and we used to take clients around there to demonstrate. And the first thing they'd say when they took their shoes off was, "Oh, I thought we had underfloor. I didn't think we had underfloor heating." You know, it warms the floor. We can get the floor up to 28 degrees, so we have the benefit of both. So we're not feeling the warmth on the head. We don't feel anything coming from above with our product. With an infrared heating panel, you will, because it's 90 degrees and it's hitting your head. With ours, it's 30 odd degrees. You don't feel it. It's balancing the MRT in the room. And literally, I mean, I put it. It's a bit chilly in the office today, so I put it on, and within like 30 seconds, I just felt comfortable in here again. You know, you just feel that thermal comfort throughout. So yeah, you are getting warm floors anyway.
And did you just mention Wonder House with a HAUS? Is that right, or did I mishear that?
No, you must.
No, I thought you said Wonder House. Okay, no, sorry. Cool. Okay, yeah, we've only got a couple of minutes left, Rich. So
okay, I'm just gonna whiz through this, then I'm just gonna show you very quickly. So this is how we specify a house. Okay, so this is the mats in there. These two are number ones. So they're connected port 1 on a transformer, port 2 on a transformer, and this will be the green transformer, which is a 2.4 kilowatt located under the stairs and so on. That's what it looked like afterwards. I won't go into that. This is the transformer. I'm going to very quickly, so we've got 2 minutes, I'm going to show somebody installing it. Is that all right?
Yeah, of course.
Quick video, saves me talking. I'm afraid I can't fast forward it, but I know it only lasts 2 minutes. So this is a void property for a housing association.
Did you have?
They'd only ever installed one mat before, so they've done one mat before this. This is their second mat, so they're doing pretty well. So we're just pushing that initial bed of wet plaster through with a dry trowel, and it just absorbs straight through the little holes in the fleece. And that's pretty much that. And then I'm going to show you one more. Oh, we've got training colleges, so we're working with United Colleges, NPTC in Wales, College of North West London, and the NOCN site group rolling this out over 937 colleges around the UK for training. 10-year warranty. And then these are some of our projects. I'll just show you pictures really. So this is zoo lodges, passive house zoo lodges, beautiful places. We've got a 1980s retrofit here. You can see it turned on in the ceiling in vaulted ceilings. That's what it looked like afterwards. This is incidentally, this is on the side actually. That should be the other way around, but that's the transformers running that. So that's taking up a little airing cupboard that they now put a clothes horse in to dry clothes. This is that house we've just seen. So this is the retrofit. These are 3 brand new homes. This was the one that had a marble floor.
All right.
That people showed around. And this Sparks here took a day to fit this house by himself using Tritec. This is the Richard Hawkes job, which is a big old church and community centre. And you can see here, this is the room, and that's what it looks like when it's lit up in the ceiling.
So with Richard's properties, do they put any other form of heating in them when
not generally? I mean, the 2 others we've done, no, but this one they are with this room, because this has got I don't know, 20-meter ceilings or something ridiculous, because it's a church hall in that one. But the other rooms, no.
Yeah.
And this is a garden studio. So you can put in garden studios and people's basements. And this is a house we built ourselves. If anybody wants to experience this, this is actually an active house, and we put the Mixergy tank in. We put a BMW stacked battery in, which is just launched. This is our transformer running the house. It's got our MVHR in there, and we've got Drytec in the ceilings. That's located up in Birmingham for anybody to go and experience it. We've got other experience centres around the country. And this is the control system. So it's a very simple, this is our own control system, very simple. It runs off an app, it's touch screen, blah, blah, blah. It's got AI in it, 10-year warranty, and that's it.
No, thank you very much, Rod. That's really
I'll talk too much.
No, not at all, not at all. Yeah, there's so much to get through there, and I really appreciate you taking the time to do that. If you share the presentation, then I can upload it, and then people can actually look at those case studies in more detail as well. So yeah, that would be fantastic. And no, yeah, like I said before, with the MVHR, we've got another talk in a few weeks, and I might just offline, I'll ping you, because it might be quite good to get you along with that guy as well. Just talk to that. James has just asked, is there any? Well, I mean, you've covered this, but you said there isn't. James has asked, is there any requirements for annual maintenance of your systems?
No, it's totally maintenance free, James. No. And the other question that somebody might ask is, what happens if you damage it? How do you replace it? We had this the other day where somebody cut through a mat on installation. We just send out some little crimps, and you scrape away the plaster where it's damaged, and just bridge it and feather in a bit of plaster on top. So it's easy to fix, to be honest with you. And once if a mat is damaged, then it's only that part of that mat that goes down. The rest of the room and the rest of the house still works. So it's not like a wet system where everything goes down if you puncture a hole in it.
Yeah.
So no maintenance on it. 10 years worth of maintenance-free heating at least, up to 50 years. So.
Cool, brilliant. All right then, Rod. No, thanks for your time, and everyone for joining. Yeah, I'll upload this to Meshwork, and I'll share the link with you, Rod, as well.
If anybody wants to contact me, I'm at rod@energycarbon.co.uk. Happy to take any questions or look at any floor plans anybody's got, or hit me up on LinkedIn. All right.
Yeah, LinkedIn. As I said about the intro, follow Rod on LinkedIn. Very interesting. Cool. Cheers then, guys. Enjoy your afternoons.
Thank you, everybody.
Thanks. Bye.
Bye.